Okay. All right. So actually, I'm gonna. I was sort of finished with this other problem, but maybe not quite. How do I make some space here? I found when this is the problem with the N02 and the N204, which is really funny because I'm working with the very same example in my other class, but with a completely different, for a completely different reason. And, I realized when I went over this myself before class that it's really kind of confusing. Like this reaction loses a mole of gas. So when you're working with the molar delta H, it's really just much easier to figure out what the change in moles would be. And this is what I'm talking about. I'm talking about when you have to find delta U from delta H and a delta N. So, so I already showed you about how you get the negative 57.12 from the heats of formation or the enthalpies of formation. I do tend to call them heats of formation. They're the same thing because it's constant pressure. So delta H is Q and it's constant pressure. But anyway, so of course, you know that this negative 57.12 that you get is per stoichiometric coefficient of everything in that equation. So in other words, per 1 mole of this N2O4, because the coefficient is 1, per 2 moles of NO2 because the coefficient is 2. So it's fairly straightforward to find the delta U0 from a delta H0, because then it's kind of easy to figure out what the delta N is. And so you would look at this equation and you would say, okay, for every 1 mole of N2O4, what's going on here? For every, it moved me. For every 1 mole of N2O4, there's a loss of 1 mole. Okay, that's why this is -1. It's also for every 2 moles of NO2, it's a loss of 1 mole. If you were trying to figure this out for the total, it would be a little bit of a more difficult job, which is why I don't necessarily recommend doing it that way. So I would say to get the per mole value, and once you have that, then, now we have 4 moles because that's what 184 grams was, 4 moles. But then you have to remember to put the 2 moles of NO2 on the bottom. This is moles of NO2. So that's, and then when you do delta U, you would start with the delta U0 that you get here, which is I actually didn't calculate this and write it down. It's negative 54.64. So you would take the, to do the delta U, that would be delta U0 times the number of moles. So it would be negative 54.64 kilojoules per 2 moles NO2 times, just per 2 moles, NO2 times 4 moles. So again, it's multiplying by 2. I did this for the delta H last time. And that comes out to negative 109.28. Whereas this came out to negative 114.2. So what happens is that the system was compressed. And so a little bit more heat was released, a little bit, the delta H is a little bit more negative than the delta U because there's a little positive work done. So a little bit of work was done on the system. It makes delta H more negative than delta U. Okay, because delta U, after all, is Q plus W. Q is delta H, that's negative, and W is positive. So this will be a little less negative than this because a positive is added to it. So, a little bit of work was done on the system. A lot of heat was released. I went over that last time, I know. And so overall, delta U was negative. So that's really the end of that problem. And then we had this next problem, which did you folks get a chance, I hope, to work on that between yesterday or between Monday and today? Oh, that's not. Nope, that's the wrong one. Here we go. Okay. So delta H for this reaction, well, the delta H0 you get by taking 2 times the delta HF0 of liquid water minus 0, right? Because these heats of formation are both 0. So that's minus 571.6. So if you have 2 liters of hydrogen, you'd have to figure out the number of moles. What did you get for that? I'm sure some of you did this problem. So just make sure, try to check yourselves, because that's why I'm going over this, so that you can figure out how to do it if I'm not around. So you would use the ideal gas law. Volume was 2 liters. And then we have 08206. And the temperature then comes out to 0.0818. So you would take 0.0818 moles of H2, negative 571.6 kilojoules per 2 moles of H2, right? Don't forget to put that there, all right? And so that comes out to negative 23.4 kilojoules. Now, is delta U the same as delta H here? And what's the answer to that question? No. What's the reason for that answer?
Is it because the number of moles of gas is decreasing?
Well, yes, I mean, that is why, but the first reason why, really, before you'd get into the how that kind of works, I would say is that work is being done. I mean, that's the big deal, right? So no, and it's because work is being done. It doesn't matter whether it's done on or by the system, it's work. Whether if it expanded, it would be different. If it contracted, it would be different. It stayed the same, it would be the same. Okay, if there was no expansion work, and that was the only kind of work that we were considering. And in this case, you are right, work is done on the system. That's because the number of moles of gas, we only care about the moles of gas because it's the gas that's making it have a certain volume. So the volume is decreasing. And let's see, let's do it here. Yeah, this problem, if you're asked to find delta U, even though you're not asked to find delta U0, although maybe I wrote it in the new version, I would always recommend that you find the delta U0 and then delta U. It's easier than going from delta H to delta U, because finding that change in moles is going to be harder when you're dealing with an amount that's not the per molar amount. That's all I have to say. That's the only reason. So what I would do is find the delta U0 from the delta H0, using delta H is delta delta. I always honestly go back to the beginning. That's just the way I do it. And this would be RT delta N. And then I reverse it. Delta U is delta H minus RT delta N. And then you could see, because this delta N is negative, that again, we have a positive work contribution, because of course this is Q and this is W, because that's the first law. Delta U is Q plus W. And Q is delta H here because the pressure is constant. It's not always delta H, that's for sure, but it is here. So listen, you don't have to rederive this equation every time. You can just remember it. I just think that when I remember it, I'm going to get it wrong. That's why I always do it from scratch every time, because I know half the time I'd write plus instead of minus there, and I don't want to do that because it's embarrassing to do that on TV like this, you know. So anyway, so see, I wrote it wrong anyway. That's a delta H there. So yeah, there. That's pretty funny, actually. All right, so I'm going to do this with the delta H0. That's negative 571.6. And then this minus RT delta N. Okay, so now this is delta N for the equation as written, right? And as written, it has 2 moles of H2 and 1 mole of O2 going to 2 moles of water, but it loses 3 moles of liquid. So delta N for that equation happening is -3. So this is going to be negative 571.6 minus 8.314 times 10 to the -3, 298, -3. All right. And this comes out to 7.432 kilojoules. And you add those up. So this is positive and this is negative, just like we said it would be. And it comes out to negative 564.2 as the delta U0. And now you can take that delta U0 and you can multiply it by, well, okay, the delta U0 again is negative 564.2 kilojoules per 2 moles of H2 multiplied by 0.0818 moles of H2 that we already figured out from earlier. And this comes out to negative 23.1. Wait, did I get that right? Yeah, and this was negative 23. So it's really not very different, you know, it's only 0.3. If you didn't worry, if you didn't keep 3 significant figures, you would never have noticed that. So keep your significant figures, all right? Okay. Now here's the thing, like, what if you wanted to do the delta? I thought about this one for a while. It kind of stumped me for a little bit. If you use this same equation, but now you're doing it with a total delta H. So that's the negative 23.4 from above. So now you have to think, okay, that's the actual amount of heat for the amount that's reacting in this particular reaction. Yeah, so how much, what is the actual, so if you look at the equation again, if you have 0.0818 moles of H2, that's the actual amount, you'll have to multiply that by -3 moles, like that's the decrease. I have no room here, this is not working. -3 moles of 0.0818 moles of H2 minus 3 moles, like, let me just say lost, just, you know what I mean, goes away. -3 moles of gas disappears per 2 moles of H2. So you have to multiply this by, you got to remember to do that. That's really complicated, but that's the actual change in the number of moles. So, this number comes out to like some crazy, 0.1227. And that's the delta N, and that's just not really helpful. I mean, that's really minus, 8.314 times 10 to the negative 3. And then you've got 298. And like I said, this delta N is 0.0818 moles of H2 times minus a loss of 3 moles of gas per 2 moles of H2. And that comes out, I believe, to 0.1227. So then you'd have to multiply that by negative point. Are you gonna, that to me, that is just too hard to figure out. Like you could, you could do it, but it's so much easier to just do the per mole one, I think, and then multiply at the end by the number of moles. That I will encourage you to do that. When you do this, it comes out to negative 23.4 plus 0.304, which is, guess what? Negative 23.1. So anyway, I thought I would go through those two problems.
So, Dr. Bowie, but we don't always multiply by the number of moles, right? Like, because in this case, we ended up dividing because it was per 2 moles, right?
We always, I mean, if we're doing this, we will always have to
We
find.
divided the delta U naught by 2 to get the delta U, right? And
what are you talking about in this previous example, or?
yes, right there, like the negative 564.7 divided by 2 moles.
Yeah.
Okay.
I did divide by 2.
Okay. And then we multiply by okay, I get it now.
Yeah, because it's not negative 564.2 kilojoules per mole of H2.
Right. Okay.
It's per the way the equation is written with the stoichiometric coefficients that are there.
Right.
Yeah.
Okay.
Okay.
Thank you.
It's a little bit confusing, this section, I have to admit. That's why I go over it so much. All right, so I'm going to move on to the next thing that I'm going to talk about today. Make sure this is the next thing. Yeah. And that is another application. Today we're supposed to finish thermochemistry, hopefully. Another Hesse's law application. And this is, it's used fairly frequently, especially for hydrocarbon reactions. If you're going from reactants to products, I showed you the path that you could take that takes you through the heats of form, that takes you through the elements in their stable form. But there's another common route, and that is to combust the reactants in pure oxygen as step 1. Another lovely contrived route that you would never take in the lab. Oh yeah, I need to know what the delta H of this reaction is. Let me just burn up these reactants and figure out what the combustion, what the delta H is. So no, that's not what we do, right? But you could do it this way, okay? So then step 2 would be the reverse of combusting the products in pure oxygen. Okay. And so, and of course, if you're balanced, it's actually minus O2. It's you going this way, it's plus O2. But, if you're balanced, then the same amount of oxygen will be used here. And so, cancel itself. So and of course you have to use gas and liquid here. And so basically we could say that the delta H0 for this reaction is, okay, so this step here is the sum of the heats of combustion of the reactants. Okay, so whatever these reactants are, 3 of them, we combust each one. We add up their, we find that the combustion of all the heats of combustion of all of them. And of course, if we have stoichiometric coefficients, we have to account for that. This is going to be the sum over I of the stoichiometric coefficient of each reactant multiplied by the delta HC0 of the ith reactant. Okay, and now that's step one. And then step two is the negative of the sum of the heats of combustion of the products. And again, these are stoichiometric coefficients. So look at this. This is the way this comes out, is that the delta H reaction is, you know how when you do it with heats of formation, it's the heats of sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Well, when you use combustion, it's the opposite way. It's the sum of the heats of combustion of the reactants minus the sum of the heats of combustion of the products. And that is simply a consequence of what the steps in this route refer to, right? This first step is combusting reactants. So it's going forward in the combustion of reactants, and reverse, right? This step, this arrow here is the reverse of the combustion of the products. So that's why now the negative sign is in front of the products one. So that's something you have to remember. This is reactants minus products when you use heats of combustion. Okay, so just keep that in mind. Okay, if you ever see a problem like that, don't get your signs wrong. If you're using the path through elements in their stable form, in other words, you're using delta HF zeros, it's products minus reactants. But if you're using the path that goes through CO2 and water, that's the combustion route, then it's going to end up being reactants minus products. So don't be fooled. All right. So I have another special problem for you. And this one has a few different parts. And it really puts a lot of things together. I mean, I don't think it's terribly mechanically difficult or even conceptually difficult. Actually, I would say it is not particularly hard to think about, oh, how do I do this problem? You know, I think it's pretty clear how to do them, but you have to be very careful, you know, especially when you do the bond enthalpy part. So I just ask, I give you one reaction here, 3 acetylenes reacting to make benzene in the gas phase, okay? So I give you now the heats of formation, but, you know, I didn't give you the heat of formation of gaseous benzene. I gave you the heat of formation of liquid benzene, and then I gave you the heat of vaporization of the liquid. So this is kind of similar to a problem we had before, remember, where, you know, you weren't given the right phase for the heat of formation. So here you're going to have to combine these. So I would say I would probably recommend that you find the delta H for the reaction to produce gaseous benzene. And then you go from gas to liquid, okay, using the heat of vaporization. Wait a minute. No, you want this reaction. So, right, no, that's the opposite. You'd form the liquid. And then you go from liquid to gas. Yeah, sorry. Okay. Yeah, so you do have to have your head on, screwed on right to do this. This next one, these are heats of combustion. So, you know, while here, when you do at least the part with these two, you do, instead of here, you do products minus reactants. Here, you're going to do reactants minus products, right? Because it's from heats of combustion. So don't, you should basically get the same answer here. Because all of these are based on experimental data. They're not based on approximations. All right, but when you get to this part now here we're talking about finding the delta H for the above reaction using bond enthalpy data. Okay, now what you have to do here is you have to figure out, well, you could decide to break all the bonds and form all the bonds in the products, or you could, I actually start by writing the simplified Lewis structures. I don't include lone pairs or anything. Not that there's any right here. So I would actually draw 3 of these and say, okay, what's going on here? I'm doing this and I'm ending up with, and actually draw it and figure out how many bonds are broken and formed. Yeah. And here's a chart, and you'll notice there are double bonds and triple bonds, and you use this data here. Okay. And then you'll see how close it comes. It is a reaction in the gas phase. So, that might be okay, but it involves a benzene. That's not going to be so okay for the reasons I talked about last time. So when I say explain the difference here, I would like you to actually explain it. Don't just give me like 6 words. People here are very terse with their explanations. I'd like you to actually explain it a little better than, don't give me, more than 6 words, please. Okay. And then this is just a question to test whether you know what a standard enthalpy or heat of formation is. So this shouldn't be too bad, but it's good practice. Okay, so that so today's Wednesday. There's 2 problems, so I probably won't ask you to have them until Wednesday of next week. Okay. Yeah. And I'll probably won't have a quiz ready for you until like the middle of next week anyway. So, and I'll give you a week to do it. So does that sound okay? If anybody has a problem with that, write me. I do give people more time all the time. So anyway, okay. So that's that special problem. It's, it'll take a little time, but it's not, I think it's too bad. So there's a couple more things that I want to talk about to finish up thermochem. And we're going to start entropy next week, which is like the meat of the course, really. But there's a couple of last definitions. And then I'm going to talk about aqueous ions, which are really their own little thing, which you'll see when I talk about it. But I wanted to give you a few more definitions. One is a lattice enthalpy. This lattice enthalpy, which we call, of course, delta H0 lattice, it's actually defined in different ways in different books. But I'm just going to define it in one of the acceptable ways. It may be different from what you learned when you took inorganic chemistry, because like I said, it's not uniform, and there are some scientists that think of it one way and some the other, but it's really just the negatives of each other. So I define it, delta H lattice is the standard enthalpy change for taking a solid salt, so an ionic compound basically, and ripping it apart into gas phase ions. So if we had MX, and of course we could have MX2 or M2X, this is a metal, I'm not going to draw every possibility. I'm just going to put the easiest one down. But here we're changing it to M plus and X minus. I could have had this being M2 plus and 2x minus, but you get the idea. Okay, so it's really the delta H for this reaction, okay, or this type of reaction, where you have this is a metal ion and a positive metal ion and a negative ion. And as you can well imagine, this takes a lot of energy. So lattice enthalpies are very large and positive. And that's because, you know, this process breaks a lot of ionic bonds. It breaks strong bonds. You know, and that's not easy to do. So it requires a lot of energy. And of course, these strong ionic bonds, it's really just another way of saying the Coulombic attraction of negative and positive charges. Okay. Now, sometimes, I don't know, when you take in organic chemistry, if you talk about the lattice enthalpy, I would think you would. And sometimes it's defined as going in this direction, you know, taking those ions and bringing them together, in which case it would be a large negative number. But I don't, you know, some books do it one way, some books do it another way. Then I've stuck with this method, all right? So that's one important delta H, and another one that's related, really, somewhat. We call the hydration enthalpy. It's not particularly related, but it's easy. It's combined with the lattice enthalpy to make something that's even more familiar. So the hydration enthalpy good. The hydration enthalpy, delta H hyd, yeah. This is the delta H for hydrating gaseous ions. You could also call it solvating, putting them in water. So for example, if you had the same ions that you just got, so you just ripped the lattice apart, you have these gas phase ions, and now you're putting them in water. So the phase changes from gaseous to aqueous. Okay. And of course, these ions don't exist just by themselves. They attract the oxygen, you know, the negative ones would attract the oxygen. This is an ion dipole force. And, you know, you will have a ton of these in water. You know, you'll have like a hydration shell even all around this metal ion, etc. Whole sphere. And of course, the same thing would happen except to the hydrogen of water molecules, and you'd have many of these as well. Delta positive. More ion dipole, etc. forces. So, you know, here you on the left side of this equation, you have these poor ions that they have nothing to stabilize them, right? There's nothing for them to, you know, attract to in the gas phase. And then you put them in water and you get these ion dipole forces. And so this is much more stable than the gaseous ions, because these are attractive interactions. And attractive interactions stabilize systems, right? We know that. So of course, this delta H hydration is large and negative. And so this is, like I said, very exothermic. And you know, a single ion dipole force is not that strong. I mean, it's about like a hydrogen bond, but there's so many of them, they add up, right? So you do end up with a large negative number. And if you were to think about the process of an ionic compound dissolving in water, if you think about it, you can think about it in terms of two steps, two crazy steps in a crazy pathway, right? You could take the salt, you could rip it apart to metal ions in the gas phase. And this delta H would be delta H lattice. And then you could take those ions and solvate them, hydrate them, put them in water to get aqueous ions. And then if you add this up, so this is like step 1 and step 2 of this crazy path, but we don't care because we only have to do it on paper. Then, you know, these things cancel and you end up with taking the salt and putting it into water. And this we call the delta H of solution. Okay. And so it's the sum of the lattice enthalpy and the enthalpy of hydration. And this is a large positive number, and this is a large negative number. So I don't know if you know anything about heats of solution, but you know, when you dissolve ionic compounds, you don't usually feel a lot of heat or a lot of cold. You know, it's subtle. They're not huge. You know, you might have enthalpies of reaction that are in the hundreds or in the 200s or even more, and you might feel quite a bit of heat. But a delta H solution is not going to be that big. And the reason is really because it's a small difference between two large numbers, basically. You've got a very large positive and large negative number. So heats of formation, heats of solution are generally small in magnitude. This is the chemist, generally relatively small in magnitude, because you could go out there and find whatever you want. There are exceptions to all kinds of things. But, you know, we're talking about in the 10s, 20s, 30s, even like less than 100 probably. And that's because these two contributions sort of virtually cancel each other out. And another thing is that the type of thing that would make for a larger lattice enthalpy, like if you had a greater charge on the ion, that would also make for a greater hydration enthalpy. So I would say that ionic charge, you know, if it's greater, then the delta H lattice is greater, but so is the magnitude of the delta H of hydration. Okay, so there's a greater attraction in the crystal that speaks to the lattice enthalpy, but also there's going to be a greater attraction to water. So the things that increase, and the same thing with size, like if you have a large size, that decreases the delta H lattice because the plus and minus charges are further away from each other, right? When they're larger, but they're also going to make the attraction to water be further away. And so it's going to decrease delta H lattice and also decrease the magnitude of the heat of hydration. So it's really hard to figure out which compounds are going to be soluble and which are going to be insoluble, which is why we don't just say, oh, you follow these simple rules, bigger things are going to be less soluble, smaller things, you can't do that. It's all over the place, which is why in freshman chem, we give out these giant lists of solubility rules and all the exceptions. It's because it's really hard to figure out. So the easiest thing to do to figure out if something's going to dissolve is to add up the published values of these guys. And if it's not too positive, it'll dissolve. If it's too positive, it won't dissolve. It costs too much energy. Well, anyway, I'm not teaching that today. So I'm just going to give you an example. Sodium chloride is a great example because they really do almost cancel out in NaCl. The delta H lattice for sodium chloride is 776. The delta H hydration is negative 772. So this, you add these up, you get 4. So it's very small. Okay. Let's see. Yeah, oh yeah, something else I wanted to tell you about this. And that is, so we know that the delta H solution is the sum of these things. I guess I might as well tell you what I teach in freshman chemistry is if the delta H0 solution is positive, but is less than about 40, then we would call that salt soluble. We'd say enough dissolves, I will call it soluble. And that's because, this dissolving would be an uphill process, but that's the energy part. There's also what I call an entropy part, which is like the natural tendency to mix. And that's because nature wants to mix things. And we haven't learned about entropy yet, but we'll start next week. But I figured I'd tell you this just from freshman chem. So if the delta H solution is positive, but not too positive, then the entropy part allows the compound to be soluble. Because, the mixing up drives the reaction to happen. But if delta H solution is greater than 40 kilojoules per mole, that's just my cutoff, it probably won't be soluble. And I would say because entropy can't overcome a really large delta H solution. And of course, if delta H solution is negative, then you expect it to be soluble, because then there's nothing goes against it going into solution, not entropy and not energy. But what I really wanted to tell you was something about the sign of the delta H solution. So if you have the same example, okay, and let's say that this delta H solution is positive. That means it's endothermic, and the heat, you could write it on the reactant side, right? Because it means it requires heat. So if that's the case, and you raise the temperature, so raising the temperature is like adding heat. And that will drive the reaction to the right to remove heat by Le Chatelier's principle. So what does that say about a compound that has a positive enthalpy of solution, what is its temperature dependence of the solubility? If you have a positive, if an ionic compound has a positive delta H of solution, it will have increased solubility with temperature. Do you see that, Corey? You got that? Yeah. You add heat, that's increasing the temperature. It's going to drive this reaction to the right, creating more products. The products are the dissolved ions. However, if the opposite is true, then the opposite will be true, right? If delta H solution is negative, then solubility will decrease as the temperature increases. And that's because you would have mx goes to m plus x minus plus heat. So you would write it, you know, if you add heat by increasing the temperature, it's going to drive the reaction. Or it's not really a reaction, but that's all right. Drives it in reverse, so it'll be less soluble. So I would say more things have positive delta H's of solution. And this doesn't just go, by the way, for ionic compounds. This is true. This, well, the delta H solution coming out of the lattice enthalpy and the hydration enthalpy is very specific to ionic compounds, but if anything that has a positive delta H solution is going to be more soluble at a higher temperature. It doesn't have to be ionic. Anything that has a negative delta H solution will be the opposite. Anyway, I thought I'd show you this graph that I also show my freshman class. And this is a plot of solubility versus temperature. And you can see how things behave all kinds of crazy ways, you know. But one thing I wanted to point out was sodium chloride. So that's this line right here. It doesn't have a very big temperature dependence. And remember that the delta H of solution was about 4. You know, and then you have ones that are really much bigger than that. And then you have ones with crazy changing slopes. Must mean that the delta H solution is changing. I think that's what it means anyway. And then you have sodium sulfate that's going downhill. Okay, so there are compounds with negative heats of solution as well. It's funny there's only one on this graph. You'd think that, because I took this out of a freshman book, you'd think they want to show more than one, but no, they just found one. So anyway, that's that for that. Yeah, so I just wanted to go over something that's actually, I think, pretty interesting. You know, when you take your chemistry book and you look in the index and you look up heats of formation of different things, there's something that, well, it's different for aqueous ions. Aqueous ions have their own little zero. They have their own little way of scaling what's large and what's small. And I'm going to explain why aqueous ions are really in a category of their own. So really what I'm talking about next is delta HF zeros of aqueous ions, you know, and why are they hard to find? Why do they require special treatment? What's the dilemma about them? Because there is one really. So this is an interesting situation of ions in solution. And this is the last thing I really talk about in thermochemistry. Like I said, on Monday, we're going to start entropy. I get that far. Yeah, looks like I'm on target to do that. So I wanted to talk a little bit about the difficulty with this. So I'll start by dissolving some hydrochloric acid on paper. in water. So take some HCl, and of course, you know HCl is a gas, and dissolve it in water to make aqueous hydrogen and chloride ions. And what Hesse's law tells me is that the delta H0 for this reaction is the sum of the delta HF zeros of the products minus the sum of the delta HF zeros of the reactants. All right, so I'm going to write that down then for this example. Delta HF0 for this reaction is delta HF0 of H plus delta HF0 of Cl minus delta HF0 of HCl. Okay, so I get that straight from Hesse's law. Now, this delta H reaction, I can measure this very easily in the lab. Well, if I wanted to. And remember, we're talking about ions and the difficulties with ions, but there's no difficulty with knowing the heat of formation of HCl. So I would look this up in a book. Let's say I didn't know anything about ions and they hadn't figured out how to handle ions yet. They're just figuring it out right here, right now, today. So what I could do is I could take this delta H of reaction and add this, so move this to the other side of the equation. Hold on, I want to make sure my notes are what I'm saying here. Yeah. And that would be delta HF0 of Cl minus plus delta HF0 of H plus. All right, and so just giving you what these numbers are, this is negative 74.85 kilojoules per mole. This guy here is negative 92.31. So this is negative 167.16, and it equals the sum of delta HF0 of the chloride ion plus delta HF0 of the H plus ion. Okay. So here's the thing. I know what the sum of the delta HF zeros of these ions are, but how can I separate them? And I know that a portion of this negative 167 is from dissolving the chloride, and a portion of it must be from dissolving the H2. But I cannot dissolve, one. I can't make a chloride ion in solution without making a positive ion in solution, right? These ions go together, and you can't just deal with a positive ion and not a negative ion. So how on earth am I ever going to separate these values? Plus and minus ions go together. I can't dissolve Cl minus without some positive ion. So that's what the dilemma is how to separate this out into, the portion that's due to H plus and the portion that's due to Cl minus. So I hope you're not expecting me to show you some elaborate scheme for how we separate these and we take into account all kinds of different things, because we don't do any of that. That's not what's done when they come up with the values in those tables, okay? What we do is we define a zero. And so we make this, we just say, let the delta HF0 of H plus equal 0. Well, that's pretty crazy, isn't it? So when you look up in the books, you know, you look up delta HF0 of H plus aqueous, it says 0 in there. And then, of course, we know that since this is equal to 0, that it's this, that Cl minus delta HF0 of Cl minus aqueous is equal to negative 167.16. That's what's in the table. This is in the table. And this is in the table. I found that mind-blowing when I first learned it. And I actually didn't learn about this until I actually had to teach this class many years ago. And I was just like, I didn't know, how does this work? Why does this work, you know? And the reason it works is because we only ever deal with changes in enthalpy. We never calculate an absolute enthalpy or anything like that. So if we start with this definition, it leads to what I would call a self-consistent set of heats of formation for all the ions. Self-consistent delta HF zeros for all ions. Okay, so if you start with that 0, how would you get the other ones then? How do you work with this? Okay, so how to get more delta HF zeros of ions from this? Well, it's really not hard to do. You could use the fact that this heat of formation of the chloride ion is negative 167.16, I think, kilojoules per mole. Yeah. So you could use that to get, say, the delta HF0 of the sodium ion. How would you do that? Well, you'd start with the same kind of thing. You would measure the delta H0 for dissolving sodium chloride. So you'd take NaCl, Na plus, Cl minus, okay, and you would measure this. And you would get, I said it was about 4, remember? It's actually 3.87 kilojoules per mole, okay? And you would look up the delta HF0 of NaCl, because that's not affected, you know, that's easy to do. It's not going to be something where you can't separate. You know, just form it, measure the delta HF0. So, so then you take this reaction here and you'd say, okay, delta H0 reaction equals delta HF0 sodium plus delta HF0 chloride, which we know, right? Because we have that negative 167 number, minus the heat of formation of solid sodium chloride. So this, so I'd move this to the other side of the equation like I did before. But now I can also subtract this. And that's going to give me what I want, the delta HF0 of sodium. Okay. And so this is 3.87. This is the number I threw down. We talked a little bit about it last time. Remember, it was a big negative number because sodium chloride is quite stable, minus 167.16 that we've already talked about. And so this comes out to be negative 240.12. And you could keep going with this idea, right? You can now use the heat of formation of sodium and maybe the heat of formation of sodium bromide and the heat of reaction of NAB, of solution of NABR. So you could do what we did here. You could do, the next one might be NABR goes to sodium plus bromide. You'd use your delta H0 reaction equals the sum, you just do like what we did before. And then you would be able to get the delta HF0 of bromide. And it would be based on that original definition that we made, the original zeroing that we did. Well, when I first learned this, it was hard to convince me, actually. I was very skeptical about this. So I decided to see what would happen if, instead of picking this definition, instead of saying, this is the zero, what happened if I picked the delta HF0 of chloride being the zero? Is that consistent? Does it give me the same delta H's for reactions? And I knew it had to, but until I did it out, I didn't really trust it. So I made a special problem about that. And it's a good problem because it's good practice to do this sort of thing. But also I think that, once you do this problem, then you could really believe those numbers and know that they work. And you could have picked any zero you wanted, but it's just most convenient to have picked it for hydrogen. So I do have this other problem. This is the last one in this. Go away, please. And this is the exploring the effect of changing the zero. So this is the typical definition, right? That the delta HF0 of hydrogen ion is 0, okay? So if you use that, and these are the all accepted values, these are published values that you find from the literature and lists. So using these numbers, you will find the delta H0 for this reaction. Okay, and then you just save that number. And then we use a different zero. And then I have you figure out what the delta HF zeros of these things are based on that new zero. And in the end, you should end up, says compare this answer to the answer you got using the conventional values. Are they the same? And what does that show? So anyway, that's the special problem on aqueous ions. So there's 2 of them for you to do. They're going to be due Wednesday of next week. And if I don't put a thing in, somebody send me an email and remind me to put that in. Okay. Right. So next week we're going to start entropy, and in time we'll get pretty, then we get to delta G, and we're doing all right. We're doing all right.